In theoretical physics, every object, every photon, every human being traces a path through the universe. That path is called a world line, a record of motion through both space and time. Unlike the simple trajectory of a baseball, a world line includes the passage of time itself as one dimension of reality. This concept lies at the heart of Einstein's special relativity, where time and space are not separate stages, but threads interwoven into a single fabric, spacetime. Before we get too deep into this topic, be sure to like this video and subscribe to the channel. This helps to bring more valuable content to the platform for your knowledge and understanding. Remember, knowledge is power. Now back to the episode. World lines are not metaphors, they are the coordinates of existence. In theoretical physics, they allow scientists to visualize events within four-dimensional spacetime. Each point, called an event, has its own position in space and a specific moment in time. Connecting these events yields the object's history. For a photon, the world line lies on a 45-degree angle, where distance and time are balanced at light speed. For us, moving slower than light, world lines tilt inward, confined within the cosmic speed limit. In 1908, German mathematician Hermann Minkowski, once Einstein's former professor, reframed Einstein's equations into geometry. Henceforth, he declared, space by itself and time by itself are doomed to fade away. Minkowski showed that the universe could be described as a four-dimensional continuum, where measurements of space and time depend on one's motion through this continuum. His diagrams of hyperbolas and light cones turned abstract equations into visual intuition, making relativity a geometric law of nature. Initially, Einstein resisted Minkowski's geometric interpretation, calling it superfluous learnedness. Yet soon he recognized its power. Minkowski's formalism provided the mathematical structure Einstein would later extend into general relativity. The notion that every observer has their own coordinate system, that time dilates and lengths contract depending on velocity, became clearer through the geometry of world lines. What began as algebra became geometry in motion. World lines are bounded by light cones, the regions that light can reach or be reached from a given event. Inside the cone lies the causal future. Outside it, influence is impossible without breaking the cosmic speed limit. This structure ensures causality, the universe's strict accounting of what can affect what. The light cone, drawn from every point in spacetime, is the ultimate traffic law of the cosmos. Special relativity predicts that moving clocks tick more slowly. This is not theory alone. It has been measured. Atomic clocks flown aboard jets run slightly behind identical clocks on Earth. Muons, subatomic particles born in the upper atmosphere, survive longer because their world lines stretch through time more gently as they approach light speed. Every high-energy physics experiment, from CERN's accelerators to cosmic ray detectors, confirms these predictions to astonishing precision. Today, relativity guides your phone. The global positioning system relies on satellites orbiting Earth, where both gravitational and velocity-based time dilation alter clock rates. Without Einstein and Minkowski's spacetime corrections, your navigation would drift kilometers each day. World lines, once abstract geometry, now synchronize entire constellations of satellites to locate you within meters. In particle accelerators, world lines become Feynman diagrams, histories of particles interacting through spacetime. Each line represents the path of a particle, each vertex an event of creation or annihilation. These diagrams, rooted in relativity, allow physicists to predict outcomes of collisions that create matter, energy, and new insights into the fundamental laws of nature. At the intersection of relativity and quantum theory lies quantum field theory, where every field excitation, every particle, vibrates within spacetime. Yet relativity's smooth continuum collides with quantum mechanics' granularity. Physicists now explore whether world lines themselves might emerge from deeper quantum geometries, such as string theory's vibrating dimensions or loop quantum gravity's spin networks. Einstein often said, "For us believing physicists, the distinction between past, present, and future is only a stubborn illusion. A world line suggests that your birth, this moment, and your final day all coexist as coordinates in spacetime, already inscribed in the universe's geometry. To move along your world line is to experience reality one instant at a time, yet the entire line exists at once. The idea challenges not only physics, but philosophy and consciousness itself." From black holes bending light to galaxies whose light reaches us after billions of years, relativity shapes cosmic observation, gravitational lensing, time dilation near massive bodies, and the cosmic microwave background's redshift all confirm that our universe follows spacetime's curvature. Every star, planet, and photon writes its own world line in this expanding cosmic fabric. World lines are the signatures of existence, elegant curves through the four-dimensional continuum that record every journey. From Minkowski's chalkboard to Einstein's equations, from atomic clocks to interplanetary probes, the geometry of spacetime connects the smallest particles to the largest galaxies. Understanding our world line is understanding our place in the universe, not as static beings, but as travelers through the fabric of time itself. If you're fascinated by how physics connects the microscopic to the cosmic, this channel is your home. Subscribe now and turn on notifications for future documentaries on quantum mechanics, cosmology, and the frontiers of science. Continue your journey through the universe, one world line at a time.